Parametric equations are a type of way to represent data or graphs of curves with an equation that looks something like this. You have like an x part and a y part. And they're together as part of the equation. And both the x and y are written in terms of a third variable, which is called t. So imagine I have like 2t and t plus 3. That's an example of a parametric equation. And the way it works is, if I wanted to graph this parametric equation, x equals 2t and y equals t plus 3, you could make a chart. The chart would have 3 columns, x, y, and t. And I could put any numbers I want in for t. I'm just going to put 0, 1, 2, 3, 4. And in this x column, I plug x equals 2t, so I get 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. And for the y column, I use this other equation, t plus 3, so 0 plus 3 is 3, 1 plus 3 is 4, 2 plus 3 is 5, 3 plus 3 is 6, 4 plus 3 is 7. Now over here, on the graph, I only graph the things I graph the points that have, for each row, the number in the x column becomes the x coordinate, the number in the y column becomes the y coordinate. So 0, 3, 2, 4, 4, 5, 6, 6, 8, 7. So, and then we kind of connect the dots. So that's called a parametric equation. Again, it has both parts. The t is what's known as the parameter, and even though the t is not involved in this graph at all, although it does tell us what order to connect the dots in, sometimes people will write like next to the point sort of what the t value was for each of those. Otherwise, there's absolutely no information about what t value, how t factors into this. T actually, it's called t. Usually in physics they use parametric equations, and t is frequently standing for time. Frequently, parametric equations have sine and cosine in them. So I'm going to make I'm going to use values that are easy for me to calculate. 270, 360. So when I do 4 times cosine of 0, I get 4. 4 cosine 90, I get 0. Negative 4, 0, 4. Here I have 9 sine t, I get 0. 9 sine 90 is 9. 9 sine 180 is 0. 9 sine 270 is negative 9. 9 sine 360 is 0. And when I plot these points, I get 4, 0, 0, 9, negative 4, 0, 0, negative 9. And the way the points came out, they came out in this order. And back to t equals 360. So it tells us that it went around, and it seems to be an ellipse, and we're going to find out whether it is actually an ellipse in a second. Eliminating the parameter is when you have a parametric equation and we try to rewrite it as an equation that only has x and y in it. Gives us some idea about what it looks like. If one of the equations is linear, so it's like x equals something t, or even more complicated, as long as there's no exponent on the t or no trig functions with the t, what we can do is we can solve for t in terms of x, so t equals x over 3. Then you can substitute that t in place of all the t's in the other equation. And we can see this is actually a parabola. So that's called eliminating the parameter, making a new equation that has no t in it. It could get a little bit harder if there's trig involved, it's a little complicated. Let's see, x equals 4 cosine t, y equals 9 sine t. We know that's an ellipse, but the trick to this type is not to isolate t, because it's not a linear equation on the right-hand side. Instead, I'm going to divide both sides by 4, divide both sides of the other equation by 9, and then I'm going to square both sides of both equations. The reason I'm going to do that is because then I would get, and then if I add these two equations together, I get x over 4 squared plus y over 9 squared on the left. On the right, I get cosine squared t plus sine squared t, but there's a trig identity that says that can be replaced with 1. So as you can see, it actually did become an ellipse after all. X squared over 16 plus y squared over 81. So you can eliminate the parameter from trig equations by trying to utilize the fact that, if you can do it, to get that sine squared plus cosine squared equals 1 of anything, including t. Introducing a parameter is where you take an equation that only has x's and y's and create a parametric equation that has t in it that somehow becomes the same graph. And if the equation is already in the form y equals y in terms of x, you can just call x equal to t, and then y would be t squared plus 5t plus 1. So if you happen to have your equation in the form y equals already, that's a way you can do that. This equation is not in that form, but we can still do the introducing the parameter by writing it like this. And since 1, you know the identity cosine squared t plus sine squared t equals 1, we could also go in the other direction. Now we have a choice here. If I could either say that cosine squared t equals x over 4 squared, or I could make, it doesn't really matter which piece you make it, but usually if there's something with an x in it and there's something with a cosine, I try to relate the cosine to the one with the x in it. Sine squared t equals y over 9 squared. Those turn into cosine t equals x over 4, and after I take the square root of both sides, y over 9, and then multiply both sides by 4, so we end up with x equals 4 cosine t, y equals 9 sine t. So that's how you can introduce the parameter in the ellipse equation. Okay, that gives you just a basic idea of what parametric equations are. There is actually on the TI calculator, if you push mode, there's a mode for, it says PAR, there's like polar, function, and then there's par for parametric. And if you click y equals on that, you get the opportunity to type in a parametric equation. When you type x, it makes it t. And then in your window, you have to not only set the x and y, left, right, max and min, but you also have to set the t value, because basically it runs through values of t and calculates out x's and y's. The t is the independent variable, and the x and y are both dependent variables, unlike in rectangular functions where the x is the independent variable and y is the dependent variable. Well, there's your basic introduction to parametric equations.